Diels-Alder reaction. Okay. And it's a type of reaction that's very, very unique. I'm just going to fix this camera. Well, I guess I just need to write just a little bit more for it today, and then it'll finally catch up with us. It's getting worse by the second. Let me put a pen here. There we go. Give something to focus on. Okay, Diels-Alder reaction is a very type of reaction. It's often referred to as a 4+2, put in brackets, cyclo-addition reaction. It's going to involve 4 p orbitals from one molecule and 2 p orbitals from another molecule. Well, alkenes or alkynes are going to be the source of 2 p orbitals, and conjugated dienes will be the source of 4 p orbitals. So dienes are going to be used in this reaction to kind of a special effect. The most basic form of this reaction, we'll just do a very, very simple one. Okay. We're going to start out with 1,4-butadiene, and we're going to draw it in this, what's called an S-cis conformation. And this is actually in equilibrium with the S-trans conformation. And the S-trans and S-cis refers to this S or single bond here. Usually with cis and trans, we're concerned with either cyclohexene rings, like this trans 1,2 dimethylcyclohexane, or maybe a alkene molecule that's trans. But trans and cis can apply here, and we can see that around this single bond, these two groups are cis to one another. Around this single bond, these two are trans to one another. We're not going to do anything with this, but it's important that it's this conformation that's reactive in the Diels-Alder reaction. Okay? That's all. The other portion of the Diels-Alder reaction is typically going to be an alkene with some sort of polar group attached to it. So we have a diene plus an alkene. We have 4 p electrons and 2 p electrons, okay? Made up in the carbon-carbon framework here. And these two things, the reason the Nobel Prize was awarded for this particular reaction, is you take these two things and heat them together. You take a diene and an alkene and heat them together. You get a 6-membered ring. Okay. So when you take a diene and an alkene, you get a 6-membered ring. Right here is a new sigma bond. Right here is a new sigma bond. Right here is a new pi bond, and we form a 6-membered ring. All in one step. This is called the Diels-Alder reaction. It's quite complex. From a mechanistic point of view, we're going to draw an oversimplification of how the mechanism works right now. In reality, the mechanism works a little bit differently, and I don't think we have enough time to talk about it today. Maybe we'll get to it. We'll just see where things go. But in short, simultaneously, these three processes all happen at once. One of the pi bonds from the diene breaks and forms a new sigma bond to this particular carbon. And if this particular bond forms, a new sigma bond is forming, this pi bond breaks and forms a new sigma bond to this particular carbon, and as that happens, this bond breaks and forms a new pi bond in between here and here. So we have a pi bond breaking, a sigma bond forming, a pi bond breaking, a sigma bond forming, a pi bond breaking, and a new pi bond forming all at once. What I've drawn here in red, you don't need to know. I'm not going to ask you, and it's actually not precisely how this particular reaction works. Instead, we're going to use this particular Diels-Alder reaction to think about constructing molecules, right? When we see a pattern, there's 4 carbons in the diene, 2 carbons in the alkene, and we make a 6-membered ring that has 6 carbons in it. There's 3 pi bonds, and in the product, there's 1 pi bond and 2 new sigma bonds. Okay, so we're going to break 3 pi bonds, we're going to form 2 sigma bonds and make a new pi bond all at once. And notice, if we were to deconstruct this particular molecule, just with a little dotted line here, scissors, if we cut them, what we see here on the right half of this molecule came from the alkene. What we see on the left half of the molecule is 1, 2, 3, 4 carbons that came from the diene.